13.189, excuse me, involves a pendulum swinging down with ball A right here, hitting a block that has a slanted face to it, and the block is connected to the spring. At the moment before the collision takes place, the spring is not stretched or compressed. The block is only free to move in the X direction here. We're told that this initial angle that it's dropped from is alpha equal 30 degrees, and that the speed that it has when it's dropped from this angle is 0.6 meters per second. Mass of A is 1 kilogram, mass of B is 2 times the mass of A, which means it's 2 kilograms. The coefficient of restitution in the collision here is 0.8, and the length of the string right here is 0.9 meters. We're told that the spring constant is 1,500 newtons per meter, and the angle of the sloped face right here is 20 degrees with respect to the vertical. What we're asked to find in the A part is what is the velocity of A after the collision here with B, and then what's the velocity of B as well. Well, first of all, we're going to start off finding out what is the velocity that A has when it strikes B, and to do that, we're going to use conservation of energy to find V sub A. So we have a kinetic energy at the top of this motion over here of 1/2 m sub A B naught squared, and then we have a potential energy that the object has with respect to this level right here. And that potential energy level, let me back this down right here so we can see this drawing a little bit better. This distance down to here is L times cosine of alpha, and the total distance down is L. So if we take L and subtract L cosine alpha, we have this little bit of distance right here. So there's my L minus L cosine alpha then for the potential energy, and that's got to be equal to 1/2 MAVA squared. The MA's will cancel out all the way across. You'll get VA then the square root of all of this right here. And when you solve for VA, you get a 1.651 meters per second in the I direction. And I'm going to store that in the calculator. The next thing we're going to do is do a conservation of momentum in the X direction right here, because there's no external forces acting on this system in the X direction. This right here is not considered an impulsive force during the collision, simply because it's not stretched or compressed at this point. This force right here is coming from the vertical direction, so it's not affecting the momentum in the X direction. So we have conservation momentum out here sub X, meaning in the X direction. So A comes in with an MAVA, B doesn't have any velocity in the X direction, and afterwards you have an MAVAX prime plus an MBVBX prime, and I'm going to call that equation 1. The next thing we're going to look at is the normal direction, and I've got a drawing over here showing X horizontal, Y vertical, normal positive in that direction, and tangential positive in this direction. Okay, so the coefficient of restitution equation is going to give us that E times VA normal is equal to VB normal minus VB normal prime minus VA normal prime, or that EV, what is A normal? A normal, see the velocity is horizontal right here coming in for A, so the component in the normal direction is going to involve cosine theta. So there's E, VA normal is VA cosine theta, and that's equal to VB normal. Well, VB afterwards is going to be only in the X direction, so its component in the normal direction would be a VBX cosine theta. So there's the VBX cosine theta for VB normal, and then I just repeated VA normal out here. Now what I'm going to try to do is to set up two equations and two unknowns where I'm going to have a VBX prime and a VA normal prime. So I'm going to call this equation 2. We're going to look at the VA tangential prime because there's no forces along that slope direction. VA tangential prime and VA tangential are going to be the same. And VA tangential, if you look at VA being in this direction right here, then the tangential part is going to involve a sine theta. So we find that VA tangential is VA sine theta, which means VA tangential prime is also equal to VA sine theta. And plug your numbers in, you get my 0.565 meters per second, and I'm going to store that number. Now I'm going to look at rewriting VAX prime. I need to get rid of this out of this term right here and get it over in terms of VA normal primes and VA tangential primes. So if we're looking for, assume that we have a velocity in this direction in the normal and tangential, then to get the X component of that velocity, I'd have to multiply the normal part by cosine of theta. So there's VA normal prime cosine theta. And then the tangential part is going to involve a sine theta. So VA tangential prime sine theta. So I got a VA normal prime cosine theta plus, and then remember VA tangential is equal to VA sine theta. So there's a VA sine theta and an extra sine theta going to give me VA sine squared theta. And then I'm going to substitute that back up into this equation 1 right here. So we rewrite 1 to be MAVA, and then we'll have MA, and then this right here is going to involve these two terms. So we're going to have VA normal prime cosine theta and VA sine squared theta, and then we repeat our MBVBX prime term right there. And then if you start grouping some terms together, this term is a known term, so I'm going to put it over in the left of this other known term. And you have an MAVA, and you're going to have a 1 minus sine squared theta over there, which converts into cosine squared theta. Then the unknowns are staying on the right-hand side, and that's MA cosine theta times a VA normal prime, and then you got an MB times VBX prime. Your coefficient restitution equation right up here, I'm going to just rewrite down here, just like it was up there. And what I've got now is two equations, two unknowns that I'm going to solve simultaneously. And when I do, I get VBX prime equal to 0.910 meters per second. And I'm going to store that answer because I need it a little bit later. And the other answer coming out of there is VA normal prime equal to minus 0.386 meters per second. I'm going to store that answer as well. Now, what this means for us, if we're calculating VA prime, we need the component of this right here squared plus this component squared and take the square root of it. When you do, you get 0.684 meters per second. The next thing we got to do is find out what angle it is. Well, if we look at the VA tangential prime, it is off in this direction. I'm sorry, VA normal prime is off in this direction because we've got a negative value for it. And tangential is off in this direction. So if we do the inverse tangent of these things, we'll end up with 124.8 degrees, excuse me, 124.3 degrees measured from the normal axis right here. If we want to be measuring from the x-axis, we need to take 20 degrees off of that. So we'd end up with 104.3 degrees then as the direction of VA. The B part wants us to find out how much the spring compresses right there. Well, the only thing moving against that spring is the velocity B, or object B, and so you look at the conservation of energy there of the kinetic plus potential, which is 0 for potential, has got to equal to the final kinetic, which is 0, plus the potential energy in the spring, which is 1/2 kx squared. So the only unknown in this equation is x. And so when you solve for that, you end up with about 33.2 millimeters.